You've probably reached that point in life where you're swimming in requirements and have roughly 5 quizzes upcoming this week. You think everything is going fine until suddenly chemistry arrived. We can help with that. On this topic, we are to discuss the integrated rate laws and equations. Every integrated rate law is used only for one specific rate. There can be lots of different rates, but we will only focus on the three commonly used integrated rate equations: the zero, first, and second orders. The zero order having a rate of k, the rate constant; the first order having a rate of k multiplied by the concentration of A; and second order having a rate of k multiplied by the concentration of A squared. You might be seeing some sort of pattern here. In finding what kind of order does your rate have, you can think of it like this: k multiplied by the concentration of A raised to the power of x, where x is going to be the order. In other words, just look at what the concentration of A is raised to. If there's zero sign of the concentration of A, then it is in zero order. It is common to see values like k equals 0.500 s raised to negative 1 or k equals 1.23 m s raised to negative 1. However, in determining the order in using the values of the IREs, it is important to remember that the zero order has the variables of k equals rate m s raised to negative 1. The first order has the variables of k equals rate s raised to negative 1, and the second order has the variables of k equals rate m raised to negative 1 s raised to negative 1. Summarizing, it is k equals rate m raised to 1 minus n s raised to negative 1, where n stands for the IRE order. Every rate law has a different equation. The zero order has an equation of concentration of A net minus concentration of A equals AKT. The first order has an equation of natural logarithm of concentration of A net over concentration of A equals AKT. The second order has an equation of 1 over concentration of A minus 1 over concentration of A net equals AKT. Take note that concentration of A net is the original or initial value because the concentration of A is not changed. T is time in seconds, K is the rate constant, and A is for the number of elements or compounds in the product-reactant equation. Comparing these equations, you can see that in comparison, the second order equation has its concentration of A naught second to be written down rather than it being first. Take note that it is crucial to memorize these three equations. Let's get down on some example problems. Problem number 1. The reaction of 2 moles of nitrogen pentoxide decomposes to 2 moles of nitrogen tetroxide and 1 mole of oxygen obeys the rate law. Rate is equals to K multiplied by the concentration of nitrogen pentoxide, in which a specific rate constant K is equals to 0.00840 s raised to negative 1 at a certain temperature. Now, the questions are: A. If 2.50 moles of nitrogen pentoxide were placed in a 5-liter container at that temperature, how many moles of nitrogen pentoxide would remain after 1 minute? And B. How long would it take for 90% of the original nitrogen pentoxide to react? To solve the problem, we applied the integrated first-order rate equation. Natural logarithm original concentration of nitrogen pentoxide over concentration of nitrogen pentoxide equals AKT. Notice that the rate law equation, rate equals K multiplied by the concentration of nitrogen pentoxide, is in first order. To answer problem A, first, we must determine the original molar concentration of the nitrogen pentoxide. Then we solve for the molar concentration of the nitrogen pentoxide after 1 minute. We must remember to express K and T using the same time units. Finally, we convert molar concentration of nitrogen pentoxide to moles remaining. The original concentration of nitrogen pentoxide is equal to 2.50 moles over 5 liters, that is 0.500 molar. The other quantities are A equals 2, K equals 0.000840 raised to negative 1, T equals 1 minute, that is 60 seconds, and the only unknown in the integrated rate equation is the concentration of nitrogen pentoxide after 1 minute. Let us solve for the unknown. Because natural logarithm x over y equals natural logarithm of x minus natural logarithm of y, we will use this logic to demonstrate the calculations of natural logarithm of original concentration of nitrogen pentoxide over concentration of nitrogen pentoxide after 1 minute equals natural logarithm of original concentration of nitrogen pentoxide minus natural logarithm of concentration of nitrogen pentoxide after 1 minute equals AKT. Isolating the natural logarithm of concentration of nitrogen pentoxide after 1 minute and plugging in the necessary values, we get that natural logarithm of the concentration of nitrogen pentoxide equals negative 21.701. Taking the inverse natural logarithm of both sides gives that the concentration of nitrogen pentoxide is equals to 1.82 times 10 raised to negative 1 molar. Take note that the inverse of ln x is e raised to ln x. Thus, after 1 minute of reaction, the concentration of nitrogen pentoxide is 0.182 molar. The number of moles of nitrogen pentoxide left in the 5-liter containers is equivalent to 5 liters times 0.182 mole per liter, that is 0.910 moles of nitrogen pentoxide. To answer problem B, we solved the integrated first-order equation for the required time. Because the integrated first-order rate equation involves a ratio of concentrations, we do not need to obtain the numerical value of the required concentration. When 90% of the original nitrogen pentoxide has reacted, 10% remains. We make this substitution into the integrated rate equation and solve for the elapsed time t. Where t is equals to 137 seconds. Let's now move on to problem number 2. The gas phase decomposition of nitrosyl bromide is in second order, with K equals to 0.810 m raised to negative 1 s raised to negative 1 at 10 degrees Celsius. If we start with 4 times 10 raised to negative 3 molars of nitrosyl bromide in a flask at 10 degrees Celsius, how many seconds does it take to use up 1.5 times 10 raised to negative 3 molar of this nitrosyl bromide? Know that the rate is equals to K multiplied by the concentration of nitrosyl bromide raised to 2. To solve the problem, we first determine the concentration of nitrosyl bromide that remains after 1.5 times 10 raised to negative 3 molar is used up. That is, the molarity of nitrosyl bromide remaining equals 0.004 minus 0.0015 molar is equals to 0.0025 molar. That is the current concentration of the remaining nitrosyl bromide. Then, we use the second order integrated rate equation to determine the time required to reach that concentration. We solve the integrated rate equation using the equation 1 over the concentration of NOBr minus 1 over the concentration of NOBr not equals AKT. Isolating T and plugging in the necessary values, we get that T is equals to 92.6 seconds. It might look hard, but as long as you try, do it yourself, and practice as much as you can, you will survive. But wait, we're not yet done. There's actually more. IREs can also be used in graphs, more specifically in plotting. You see, though you can compute theoretically on what time this will become this or that, once you plot on how these changes can occur, there will be deviations. Let's say you have 3 graphs, one for each equation: the zero order, first order, and second order. As you can see, there is only one graph that is linear, and that's the second order, meaning it is the equation that is the most accurate for that equation. Though there are some cases where the graphs are not that linear, the best thing to do is to use the equation that looks the most linear of the three. Also, take note of the linear slope equation y equals mx plus b, where y is the final value, m is the slope, and b is the y-intercept. This following data can be changed into the given summarized table. And tada! We're done! I hope you've learned something about integrated rate laws and equations of the zero, first, and second orders. For those who are doing cram reviews, we wish you the best of luck.